So now moving into high performance challenges, and Jim Cownie, who's supported the Multicore challenge for a number of years, is going to speak from Intel. So I hand over to Jim.
Yeah, I've been coming to these for a few years, and as I frequently do, I made the mistake the first time of not keeping my mouth shut. So I came as an attendee and asked questions, and so then I started getting invited to talk. And this year, he stitched me up with 2 talks, which I wasn't expecting. I was expecting 1 and the panel session, which would have been nice and easy, but I got 2. So there's half of an argument here, and there's a continuation in a slightly different direction later in the afternoon if you want to attend that one. As it says here, I'm a principal engineer, which means, well, the main thing I learned about that when I went on all the training courses and everything was, you can't say those stupid who run the company should any longer, because now you're one of them. So supposed to be responsible, I take that with some grain of salt. SSG, just to give you a little idea of where I'm coming from before you start asking me about transistor characteristics and process and things, because I know nothing about that. SSG, Software and Services Group. DPD, Developer Products Division. So software is that S there, right? So software is my stuff. DPD, Developer Products Division, is the group within Intel that makes software that we actually sell and you pay money for, like our compilers and those kinds of things, the VTune tools that we'll be demonstrating this afternoon in some of the demos. And TCAR is Technical Computing Analyzers and Runtimes. So they decided that they would give these different groups some kind of market orientation. And so technical computing and analyzers and runtimes is what we actually do, but we think about technical computing. So that's why I'm talking about high performance, because clearly high performance is technical computing. What did I do? I hit the wrong button. Okay, try that one. Okay, moving on to the actual subject. And I promise you, I had no collusion with Dave May, right? It looks very much as if I did, but I really didn't. We really didn't discuss this at all. So why is heterogeneity a challenge now? Well, we've had it forever. And I happen to have chosen almost the same kind of examples that Dave did, 360 channel adapters, 1964, CDC 6600 peripheral processors, also 1964, the FPS array processor. They did very well for a while. They attached, I think TTL built originally array processors doing fast floating point operations onto PDP-11s, and they went down very well with people like the oil exploration people, because they could stick some of these on a ship and actually take them out and do an initial analysis and check that the data that they were taking from rare explosions in the sea actually gave them some decent measure of what was going on. And similarly, things like synthetic aperture radar and so on, very, very popular in those areas. And coming more modern and back into the Bristol thing, ClearSpeed, SIMD processors in 2005. So we've been doing this for a long time. And my conclusion, just the same as Dave's, is that unless it's doing something really different, it tends to go away, right? We don't really, the peripheral processors, the channel adapters, those are still going, they still exist. But the compute parts of these things tends to get eaten up by the CPUs. And that's partly because of the Moore's law issues that we were describing earlier. And partly it's because it's a pain programming these things if they're so different. You want to have homogeneity, because that makes it easier to program things. So what are the real challenges for high performance? Well, bandwidth, power, programming models are the ones that I think are most important. And so bandwidth we'll get onto a little more in a minute. Power, again, we'll get onto a little more in a minute. Programming models, well, there's an awful lot of old code around. And if you go out and you look at the kinds of codes that people are running, you can trace them all back a long time. And a huge amount of it is in Fortran. Probably 70% of the codes in HPC are in Fortran. That is kind of frightening, because computer science departments completely ignore Fortran, right? They view it as a dead language. Oh, Fortran 66, well, maybe I did something with that. It isn't. It's a modern evolving language. and it's frightening to hear the people who write the compilers don't even, I hate to say this, I was at an Intel internal thing and someone stood up and said, well, none of our languages support parallelism. None of them has an unordered loop. Fortran has had do unordered since 2005, right? So, and co-array Fortran, which is a distributed memory system, has been around in the standard for a long time. But people ignore these things. Fortran is taught in engineering departments very sensibly. You're teaching students who are going to go and work out on this large corpus of code, right? They need to understand it. Going out and saying, oh, I can optimize C++. Great, but we've got this Fortran code. They're doing the right thing. But as computer scientists, we're kind of ignoring that. So preserving investment in existing code is important, and ensuring that new code has portability into the future. So it's all very well to say, well, here's this great new language, I'm going to use that. That gives me 20% performance today improvement, 200% performance improvement today. But if you're then tied into that, if that language then dies, well, that was a waste of time. So just slightly, does heterogeneity help with any of these? Interesting question. Let's see what we think. So here's the great graph. This has everything on it. if you can read it. So what we're plotting here is time along the bottom here and exponential logarithmic growth up the left-hand side, and these are all relative numbers, okay? What we've got on here. So first, this black stuff, it's a bit hard to see, but it's the squares, is the number of transistors we can make. So this is Moore's law coming up here, right? This data is all from CPUDB, so it's all public data. You can go find it. Google CPUDB if you want to find this stuff. So here's Moore's law. It's keeping on track more or less. I mean, there's a bunch of scatter here because we've got lots of different people manufacturing things and they can do different things at different times. So I was kind of amused to see FinFET coming in 2014. Well, we've had that since last year in the Intel process. So Moore's law carrying on. That's great. We're going to have all these transistors. Then we've got in red is the relative clock speed of processors. Well, that's kind of tracking up. It's not on quite as steeper, Moore's law is coming up like this, and this is coming up a bit shallower. But then here, 2000, 2004, it turns over, right? We're flat. The clock speed isn't increasing any longer, right? We've hit a limit of clock speed. We're not going any faster in our processors. And that is partly because of the green triangles. So this is the power that we're dissipating. And again, that's going up and again on a slightly slower line, but you'd expect it to be up here now, and it isn't. It's completely turned over, and it's even, it's even coming down again, right? So that is related to the clock speed. We can't go any faster. We're power limited. We're stuck. The blue ones are the performance of the processors. So that's, I don't know, spec int or spec something, some measure. I honestly can't remember, but CPUDB will tell you, right? And that is going up, and it is managing to keep going up slightly, but it isn't going up as fast as the number of transistors, right? The number of transistors is going up. And this conforms somewhat with a law whose name I can never remember, which is from an Intel fellow that says that it's another observational law like Moore's law. His observation was that the performance of a scalar processor goes up as the square root of the number of transistors that you put into it. The square root, or the amount of energy that you put into the processor. So a sea of very small processors is better than one large processor. Well, that's the converse of that is Seymour Cray's observation that he knows how to harness 4 horses to pull a cart, but he doesn't know how to harness 1,000 chickens. And so we've hit this power and clock limit, and we're going to have to do something else. So we've hit limits in all of these things, but not in transistor budget. So that was my Moore's law slide. I didn't have more on there, but that was my Moore's law slide. Getting back to bandwidth, this is from John McAlpin's stream database. Again, you can find this on the net and analyze it. What I'm plotting here is machine balance, where machine balance is flops divided by bandwidth. So to do A equals B op C, you need a balance of a third, right? And this is from main memory. So you can see that back in 1991, we were down under 1 on the balance, right? These are for real machines, right? All the machines that came out and that he measured in the year are plotted on here by the year. And you can see that we started off, well, we had some machines under 1, and now the best machines are over 10, right, in balance. So you have to be doing a lot of operations, a lot of floating point operations for every load that you do. Otherwise, you're not going to get the performance. To some extent, this is a result of people deliberately building unbalanced machines, right? And that's the result of, and I can blame that on Jack Dongara, as Dave somewhat was, because LinPack, you can run LinPack with no memory bandwidth, right, as long as your cache is big, and over a piece of wet string, as long as you have enough memory space, right? Because it's doing very dense linear algebra operations, and you can arrange it. So if you want to build a machine, if your customer wants you to build a machine that is there to get in the top 500 and do LinPack, then you put in huge number of floating point multiply add units, and you don't put in as much memory bandwidth. And in some ways that's justifiable, because those transistors, you probably can't have them all turned on anyway most of the time, so you might as well put them down as ALUs, as FMA units, and then the people who can use them, and the other people where it didn't cost them very much. Of course, I would follow Dave and say they should be used in communication engine, but marketing people have these funny ideas. So, well, they want to sell the machines, right? And if the customer's coming and saying, I want a machine to get in the top 500, they're the ones with the money. Follow the money. So everything's getting worse in bandwidth, and that's going to hurt us. So we now need more than 10 ops per load or store to achieve peak flops, which is pretty horrible. So how do we solve bandwidth? Well, you use the fastest available memories you can, GDDR5. And here's a quote from John Gustafson at AMD that I came across on the web recently. You know, the real secret sauce for Xeon Phi, which is the Intel high-performance computing part, and GPUs alike, is the use of GDDR5 memory instead of conventional DRAM. So I quote anyone. I'm quite happy to quote AMD, and I think he's right. That is the difference. So the other point, though, is you've got to use your limited bandwidth well. So you have to reuse data. You need caches. The caches aren't there because of the programming model. They're because of the fundamental issue that accessing memory from off-chip and putting data back to off-chip is extremely expensive in terms of energy. It's slow. Well, you can get around that with a streaming architecture. I mean, but to get over it, to get over the energy cost, you have to reuse the data. And you have to operate on all the data that you fetch. This is the awful problem with C and C++, that they really push you. The language really naturally makes you write things as an array of structures. So I define some structure that is a point or whatever, and I integrate that in my star or whatever it is, which has a mass and a position. So I have X, Y, Z mass for the thing, and then I have an array of them to represent a galaxy, right? And now I want to do some operation like compute the average mass, right? Those mass elements are 4 words apart because I've got 3 other things next to them. So whenever I fetch one of them from memory, I bring in a cache line, I fetch the whole thing, and you have to fetch at least, you can't go, oh, well, just use the memory system a bit more efficiently, because the DDR5 is wide memory anyway, so your memory system has to be wide to get the bandwidth. And so you're pulling in a lot of data that you're not using, so you're wasting your memory bandwidth. And that's a problem with the programming language, right, in that it encourages you to write in that array of structures form rather than a structure of arrays form, which is how we would have done it in Fortran 77 because it's all we could do, right? So you have to operate on all the data that you fetched. And, spend money, well, that's okay. we're not, you know, there was a joke a long time ago that, or an observation that bandwidth is easy. You just put in lots of wires and you spend money. And latency is hard. And that only IBM could solve that. And that was because the speed of light was different in Poughkeepsie. So locality is critical and become even more so. And I'm sorry, but I don't believe that streaming architectures can scale. Because I think that I have a slide in another deck that uses NVIDIA numbers for energy consumption. And that I believe shows that. Well, I didn't put it in this deck. So coming back to power, where are we actually? Well, the current #1 in the green 500 is this machine at NIST called Beacon, and that's an Intel machine with Xeon Phi. Ooh, I forgot the Intel brackets. They'll shoot me. I got the TM on the Phi though. And that achieves 111 impact teraflops, and it's at 2.49944 gigaflops per watt. They actually quote it in megaflops per watt, and then there's the 0.44 looks more reasonable. I would feel justified most of the time in rounding that to 2.5. And the Chanhei 2, which there's been a lot of noise about recently, a big machine in Japan, expected to be #1 in the top 500 this year, coming next. The closure date for submissions to top 500 is this Friday, and that Jack Dongara's been and seen this machine, kicked the tires, and it's achieving 30.65 petaflops in 1.9 gigaflop per watt. So taking the top, this one, the Beacon one, an exaflop machine would be 400 megawatts. That is really implausible, I'm afraid. So we need to find 20x per foot improvement in our efficiency, in our energy efficiency from somewhere to get to an exaflop. And if I flip back to that other side, you would see that even though our efficiency is improving, it's not going to get us anywhere near there. Again, back to the programming, old, Fortran, 70%. There are some standards, so I slightly disagree with Dave here. There are standards and they are evolving, things like OpenCL, OpenMP. OpenMP supports OpenMP 4 when it gets passed, which it will do within the next month or two, I believe. Certainly there was a meeting in Toronto last week and they voted through most everything. And I didn't mention MPI here, but MPI is a pretty common standard for message passing between the clusters, between the nodes in an HPC machine. And the standard languages target the CPU as well as the co-processors. And the really nice thing with that is that the optimizations like vectorization and parallelization help on the CPUs as well as on the Xeon Phi machine. So they're not wasted effort. So does heterogeneity help? Well, there seems no real reason for heterogeneity in the instruction set architecture, but implementations are different because they do different things. So we use GDDR5 on the Xeon Phi. We use standard DRAMs on the normal Xeon processors because the GDDR5 is too expensive to be the mainstream memory technology. So we have exactly what Dave was talking about, a common instruction set architecture, and that's true right down from the Atom processors, like the one that's in my phone, up to these other things. And there are new programming models like OpenCL, OpenMP4 that allow portability between co-processors, CPUs, and hardware vendors. And these properties of your program, you need to be parallel, you need to vectorize, you need to optimize bandwidth, are going to apply everywhere. So my conclusion is that heterogeneity probably doesn't help for HPC. And I should probably show you the legal disclaimer.
Okay, brilliant. Thanks, Jim. Any just slight ripple of applause? Right. We couldn't hold them back, Jim. Any questions? Any questions on that?
I'm around all day, so.
Yeah, and you're in the session later as well, as you said.
Yeah,
you got 3.
Yeah, there is one.
Oh, there is one. So.
Sort of related to your point of software lasts for a very long time. What do you see the future of Intel threaded building blocks? So basically, if I wrote a piece of software using that now, would I still be expected to be able to compile and run that software in 10 years?
Well, it's all standard C++. It's all open source. You have all the sources. If Intel went bust tomorrow, you would still have all the sources and all the rights to use them. We're very keen to keep enhancing it and continue working on it. We have more people working on it than we have working on the OpenMP runtime, which is, I'm the architect for the OpenMP runtime, I should just throw in there. But there are more people working on threading building blocks than there are on OpenMP. So in terms of your security, take a copy, screw it somewhere, do whatever you do, carve it on tablets to make sure you're convinced that it isn't going to disappear. And you're absolutely safe with what you have. If the C standards change in 15 years in an incompatible way, well, I can't do anything about that. But we're absolutely committed to it, and you have the freedom to archive it. So I think you're pretty safe.
Thanks.
Well, do you want to set down?
Yeah, Dan could shout.
We're almost on the same thing then. Is it worth carrying on to using MPI?
What would you use instead?
Co-Ray Fortran?
If you can get performance, go for it. I have so I'm an MPI guy. I was in the MPI 1 standards committee, and again, I foolishly didn't step back or open my mouth when I should have kept it shut. So I ended up being the chair for the profiling subcommittee and wrote that part of the document. MPI is a big standard. Everyone supports it. I don't see it going away. It will evolve. It is evolving, but I can't see any HPC vendor not supporting MPI in the future.
But does that mean the future then is a mixed? All codes will have MPI in them, OpenMP in them, co-processing stuff in them?
No, of course not all codes, because people do different things. But existing codes, as we were saying, have long life and will continue. Those ones will continue the way they are, right? New codes, maybe there's a bunch of interesting work being done by people at Berkeley and Stanford, and also some of the Warwick Imperial people are looking at interesting things to do with taking higher level languages like Python and having, I'll talk about the Berkeley thing because that's the one I know the best. They have this thing called CJIS, Selective Just-in-Time Specialization. So the idea is that you introspect in Python and then you generate code on the fly for the machine that you're actually on based on the actual parameters of the problem you're looking at. And that lifts you to, and so you write code that looks like it's just NumPy code, right? Except then you can compile it on the fly based on the actual properties of the problem that you have, the array sizes you have, and so on. And at least you're not in the problem of SOA versus AOS, because you don't have any addresses and you don't know what the data layout is, so you can optimize that. So there are interesting things there. Whether they're ready to be written, whether major codes are ready to be written in them, is unclear.
Thank you very much, Tim.